So we're talking about bridges and collision domains. So if you have a network with these number of devices connected in a bus topology or even a star, we have 10 devices, 12 devices, sorry, here. And we are talking about 10 megabit per second standard Ethernet. So if one device has got data to send, it can use the whole bandwidth. It can use that 10 mega. But if there are, for example, two devices that want to send data, then this data rate will be shared among them, because if one device sends, the other one cannot send at the same time. So the actual bandwidth will be divided by 2. If all of them have data to send, then the bandwidth will be shared among all of them, which is 10 by 12. So the actual data rate will be much lower than the full available data rate. To increase the performance of the network and make the data rate, actual data rate higher, we normally use bridges. So the bridge will divide the collision domain. Before we had one collision domain, now we have two collision domains. So in this setting, in each collision domain, how many devices? 1, 2, 3, 4, 5, 6. 6 devices, and the bridge port also is considered another device. So we have 7. So actually now the data rate will be divided by 7 rather than by 12 as in the previous setting. So here the actual data rate will be divided by 12, but here for this side will be divided by 7, and this one also 7 by 7. Therefore it's better, of course, to have smaller collision domains. Even if you subdivide it, put a bridge here, you'll have better data rate. In this case it will be 10 by 4. 1, 2, 3 and the bridge port. So 10 by 4 is better than 10 by 7. 10 over 7 is better than 10 over 12. Therefore it's desirable to have smaller collision domains. Instead of the hub or the bus topology, here for example, you can use a a switch in a star topology. In this case, you have how many devices? 1, 2, 3, 4, 5, 6, 7. 7 devices. So you'll have 7 separate collision domains. If this was a hub, it will be, all of them will be a single collision domain. But now we have 7 separate collision domains. Each collision domain consists of the device and the switch port. So the data rate in this case will be 10 divided by 2, which equals 5 megabit per second. Full duplex Ethernet. One limitation of these implementation are the duplex mode. It's actually half duplex. You cannot send and receive at the same time over a bus topology. You either need to send or receive. So this is a limitation. The next step in the evolution was to move from switched Ethernet to full duplex switched Ethernet. So now this was a switched Ethernet, this one, but it's, you see here, it's half duplex. So there is still collision domains, okay? Half duplex, because this can send or receive at the same time, because you have this port also. So you cannot benefit of the 10 megabit per second bandwidth. The actual bandwidth will be divided by 2. But with full duplex, the or the full capacity of the will be available to you. So in this case, for example, if you have 10 megabit per second, you can use the full bandwidth capacity. There are two links, the station and between the station and the switch, one to transmit and another one to receive. Okay, so in half duplex you either send or receive. In full duplex you can send and receive at the same time. There is no need actually for carrier sense multiple access collision detection because there are no collisions. The transmission channel is separate from receiving channel. Therefore, there is no collision. But actually, we still use this for backward compatibility issues. Each link is point-to-point, dedicated path between the station and the switch. So you have point-to-point links between that's the full duplex. So the next step in the evolution of the Ethernet was, as we studied this, we studied this standard. Now the next step was to increase the data rate to 100 megabit per second, which is called fast Ethernet. So fast Ethernet is covered in this standard. The goals of fast Ethernet can be summarized as follows. Upgrade the data rate from 10 to 100 megabit. Make it compatible with standard Ethernet. So this one, if you have one device that works with standard Ethernet, it still can work or negotiate with devices working on this standard fast Ethernet. Keep the same 48-bit address. We said the physical address, which is called MAC address also, we'll use the same physical address. Keep the same frame format. So the Ethernet frame format for standard Ethernet and fast Ethernet is the same. Keep the same minimum and maximum frame lengths. So we still need to adhere to the same minimum and maximum lengths of the frame. The fast Ethernet MAC dropped a bus topology, okay? So we have no longer a bus topology in the fast Ethernet. We only use star topology. Okay, bus topology only in the standard Ethernet. There are two choices. So if you use a hub, then you will use full duplex and you need you'll use half duplex and you'll need carrier sense multiple access collision detection. But if you use a switch, then you can use a full duplex approach. In this case, it's not required to use carrier sense multiple access collision detection, but it's kept for backward compatibility with standard Ethernet. Because if you don't use this and you connected a device using standard Ethernet, then it cannot work because it only uses this protocol. So you have to, if you want to keep backward compatibility, you have to still use the carrier sense multiple access collision detection protocol. Fast Ethernet also introduced auto negotiation. So what's auto negotiation? We have now, for example, some devices working on 100 megabit per second, and some other working on the standard Ethernet format, which is 10 megabit per second. So how to negotiate data to because if these devices want to communicate, this can send and receive at 100, but this only can, so you have to negotiate what speed they can communicate. So they will choose 10 because this one can work on 10 and this one also can switch to 10. But if they choose 100, this one cannot process data at 100 megabit. So they have to negotiate what data rate they should work. Auto negotiation was designed particularly for these purposes, to allow incompatible devices to connect to one another. So 10 and 100, they are different standards, but they can. For example, a device with a maximum capacity of 10 megabit per second can communicate with a device with 100 mega, but which can work at lower rate. Of course, this 100 will switch to lower rate so that it can communicate with this 10 megabit per second device. To allow one device to have multiple capabilities, of course. So this device can communicate with another one of 100 megabit per second or a device with 10 megabit per second. To allow a station to check a hub's capability. Hubs also, or switches also have data rates. So the switch may support 10 megabit or 100 or 1 giga. So the auto negotiation, before the communication starts, the device will check what data rate this hub or switch can support before starting communication. If there are only two stations, they can be connected point to point. You don't need a switch or a hub. You can connect them directly. We'll do some labs on these. 3 or more stations, then you need to connect a switch or a hub. Normally hubs are no longer used. We always will use switches, so we'll use full duplex communication. So if you have only 2 devices, you don't need a switch or a hub, but if you have more, then you need to add a switch or a hub. So what about the physical layer implementation, the cabling of fast Ethernet? Fast Ethernet implementation at the physical layer can be categorized as either 2-wire or 4-wire. The 2-wire implementation can be either Cat5 UTP, which we studied before, which is called 100 base TX. 100 is data rate, baseband communication, and T for twisted pair. Or it can be fiber optic. You see here 100 base F. F means fiber. The 4-wire implementation is designed only for category 3 UTP. We don't use it actually that much. This is the most widely used category, 100 base TX. So 100 base TX uses either UTP, unshielded twisted pair, or shielded twisted pair. The maximum length is 100 meters. It uses 2 wires. This is the physical and the line coding. I think you studied line encodings. FX uses fiber, and the length is about 200 meters. It uses 2 fibers. Base T4 uses all 4 wires, and it's UTP up to 100 meters. Now the next step in the evolution of the Ethernet was the gigabit Ethernet. Gigabit Ethernet works, as you know, at 1 gigabit per second. It's covered by this standard, IEEE standard. So if you want the specifications of this protocol, or you go to IEEE standards and see this standard. It covers all the details of the gigabit Ethernet. The goals of gigabit Ethernet design are: upgrade data rate from 100 to 1 gigabit, 100 mega to 1 gigabit per second. Make it compatible, again, you see this is important, with standard or fast Ethernet. So even though it's a 1 gigabit, it can still work with 100 megabit per second, or fast Ethernet and standard Ethernet. It still uses the same physical address. The MAC address is still same, and uses the same Ethernet frame format, and keeps the maximum, minimum, and maximum frame lengths. So all the same, the physical address, the frame format, the lengths of the frame, minimum and maximum. And still also supports auto negotiation as defined in fast Ethernet. So auto negotiation is important because there may be devices working at 100 mega, others working at 1 giga, others working at 10 megabit per second. So auto negotiation is important to adjust the data rate between these different devices. So gigabit Ethernet uses mostly full duplex, and no longer we use actually half duplex. A central switch connected to all other devices. In this mode, each switch has buffers for each input port in which data are stored until they are transmitted, because sometimes when you have lots of data, the switch needs buffer to store the data so that it can process the data. There are other switches that use and send data instantly without storing them. There is no need for carrier sense multiple access, as there are no collisions in this mode, because you are using full duplex. So there is no need for this protocol. Half duplex is also supported, so that gigabit Ethernet can be compatible with previous generations. A switch can be replaced by a hub. Carrier sense multiple access is used in this case. So even with gigabit Ethernet, still carrier sense multiple access collision detection is supported, and you can use it if you use a hub. So you can connect fast Ethernet devices, standard Ethernet devices, gigabit Ethernet devices together, and they will all work without problems. But of course, the auto negotiation would come into play, and only the data rates, for example, if this one is 1 gig and this is 10 meg, they will auto negotiate the speed, and they will use the 10, not that 1 gig, because this one cannot process data at 1 gigabit per second. But this one can process data at lower rates. Gigabit Ethernet topologies. If you have again two devices, you can just make a point-to-point connection, and you don't need a switch or hub. If there are two or more, you can use a switch. You can use, you see here, a switch another network, and then connect them together. You can use hierarchical topology here, for example. You see, this is a hierarchical topology. So two stars connected with a switch. This is for redundancy. You can go this way, or if this connection is broken, for example, you still can use this path to communicate. We'll study these when we study spanning tree protocol. Okay. Now the last, the implementations, the gigabit Ethernet implementations, it can be categorized as a 2-wire or 4-wire implementation. The 2-wire implementation uses fiber optic cable, 1000 base, actually we sometimes use it 1 gig base SX, 1000 base LX, S for short wave, L for long wave, or STP, 1000 base CX. 4-wire versions use category 5 twisted pair, you see, UTP cable. So it's this is the most common used actually. It's 1000 base T. So SX is fiber, LX fiber. Both of them use fiber. Short wave, this one, long wave. Base CX uses STP, shielded twist pair. Base T uses UTP. You see the distances for fiber. Long waves can go up to 5 kilometers, but the standard 1000 base T is the most widely used. We can go up to 100 meters. It uses full duplex, all 4 wires. Now the last standard is the 10 gigabit Ethernet. It's released under this name, 802.3. You see all of them, Ethernet start with this 802 point something, 0.3. Ethernet all is 0.3. So these are the letters that specify the rate and the goals of this standard are to increase the data rate to 10 gigabit per second, make it compatible again with standard, fast, and gigabit, so they can all work together. Keep the same physical address or MAC address, use the same frame format, and keep the same minimum and maximum frame lengths. So again, all the same before. Allow the interconnection of existing LANs into a MAN or WAN. Of course, make Ethernet compatible with technologies such as frame relay and ATM. We will not study these. And here is the last slide. So the implementations, 10 gigabit Ethernet, sometimes we refer 10 GBE, operates only in full duplex, so no longer for half duplex used, which means we don't use carrier sense multiple access collision detection. Some common 10 GBE over fiber implementation are 10G base SR. S means for short range or short reach. Short reach, you see, is about 300 meters the length, and there is a LR, the long reach, can reach up to 10 kilometers, Okay, so this is actually uses single mode fiber, and the short reach uses multi-mode fiber. We have also the base at 10G base EW uses also single mode. It can reach up to this extended, can up to 40 kilometers. You don't need repeaters for up to 40 kilometers. You can go between two cities without using any repeater. This is very important because you can connect LANs and WANs together. 10 gigabit Ethernet can also be implemented using copper. Okay, so the next promising standard is the 10 GB base T, which uses the same RJ45 connectivity and can provide 10 gigabit beta. Of course, it's still not very common, this standard, because of some power issues, because to achieve this rate with this standard, the power consumption is a bit high, which is still not very, therefore it's not very common. It can use UTP or STP. So standard UTP or CAT, actually we use CAT6A. Okay, it can reach up to 100 meters. And there is, this one is in use, but it's not very common again because of the bulkiness of the cables and connector. Uses this copper cabling and work up to 15-meter distance. You can see how this actually this is a promising standard which will dominate in the coming years. But for fiber there are many implementations. These are actually this is used in backbones and for interconnecting LANs. So this is our lecture today. Thank you.